So welcome everybody to this Christmas talk. Also welcome to Dresden. We have a particularly burning topic today, which is a mixture of information technology, signal recovery, and machine learning. Things very hot topics. And at least here in Hamburg, we enjoy the pleasure of real Dresden Christstollen, which was imported yesterday from Dresden and was cut with love by Raphael. So enjoy.
Okay, so thank you very much for being here. So welcome to the Christmas presentation of this year. This talk will be about, if this works, will be about the journey and lessons learned from development machine learning models in the context of unraveling LoRa frames under collision. I would like to first start with some disclaimer. First, I'm really not a machine learning expert. This is something we just started giving a look during this year. We have some kind of background about the stuff I wouldn't consider close to being an expert. So just to let you know. And also there might be, well, math formulas that appear in the area, but don't worry, they're like passing clouds. You can glance at them, but you really don't need to give them a second thought. So since we're talking about LoRa, let's define what it is. This is a proprietary wireless modulation technique that has long range, up to 15 kilometers, using very low power consumption, but of course at the cost of very low data rate in the order of bytes per second. And LoRa has very interesting use cases. Most of them have to do with tracking elves to ensure they don't slack while packing presents for children. Also has been used as a now-nice monitor, for instance, for people that use tabs instead of spaces. They don't receive presents during Christmas. And also LoRa has shown very good results already near health tracking, which traditionally used cellular networks, but got really expensive because of roaming outside of the North Pole. So LoRa is being replaced now in these cases. And to describe the problem, here's so this with the mean arrival rate of LoRa frames in selected urban areas, assuming that the population, each person has 10 devices, and these devices transmit 1 message per hour. Since these devices can transmit more than 10 kilometers, here we see, for instance, that just in Berlin, we would get around 3,500 packets per second on a gateway. And while there are some fine techniques we can do, such as defining different channels, this could mitigate the problem, but the thing is that the long range yields a high collision probability in the case of LoRa. So the remainder of the talk, we will see what happens when LoRa frames collide, why this is a problem. Then, of course, we will begin this journey and explain why we try to switch to machine learning and also how this process went, the process where we finally saw the light, and the lessons learned of this whole journey. So first, in order to understand what happened when the LoRa frames collide, it's important to understand actually how LoRa frames look like, and especially how symbols look like. The LoRa modulation uses chirps as symbols. So using a technique called chirp spread spectrum, this means that the frequency of the signal varies linearly over time, as we can see here. And these chirps are just complex signal, which doesn't mean they're sophisticated, but rather that they have a real and imaginary part. And these both parts are transmitted using carrier waves. So basically, we encode this imaginary and real part on transmission. And what LoRa does is encoding the symbols by cyclically shifting the chirps, as we can see here. These are the same chirps that just are wrapped around. So basically, just by shifting this chirp, we can encode different values. The question is, how do we get back the encoded value? What the receiver does is multiplying this received frame with down chirps, which are essentially complex conjugate of the base chirp, and it generates the so-called chirp symbol, which have constant frequencies, so they're just complex sine waves. What do we do then with this complex sine wave? We can just extract the frequency by applying the fractional Fourier transform, the fast Fourier transform, and with that we get the frequency spectrum. And if we find the frequency being with the highest magnitude, then we will already get which is the symbol we're encoding here. And this is very nice because when we do this downstream multiplication, this doesn't correlate with the noise. So it means that all the energy is concentrated in this peak. And this means that it can decode symbols even below the noise level. And this is the reason why LoRa can transmit up to 15 kilometers. But in the case of collisions, what happens in the end is that a fraction of the symbols will appear in the chirp symbol, as we can see here. And what happens in this case is that we will see a full sine wave and some partial components here, called partial sine waves. And in the frequency spectrum, here we see the actual symbol, but we will see also in the location of the partial sine waves some peaks. And of course, if these peaks have more energy than the true peak, then the decoder will actually decode the wrong symbol because the true peak is actually here. So the problem with this is that basically the baseline decoder may not detect symbols under strong signal interference. There's already related work for trying to recover LoRa symbols in collision. But the thing is, most of these algorithms have a trade-off between accuracy and real-time performance. Most of the real-time performance is because many of these algorithms require a structure of the whole frame. So basically, you need to know what happens with other LoRa frames that are colliding at the same time. So you cannot decode symbols in real time. And those that can decode in real time have a very low accuracy. So you would like to have something that you can run in real time, but also have an acceptable level of accuracy. So this whole problem is just finding the full sine wave in the chirp symbol. And as we mentioned before, there can be only one because this is the one that corresponds to the actual decoding symbol. So at this point, we decided to start the journey with the most obvious step, which is first gathering symbols to see how this looks like in practice. For that, we used two strategies. First, we had an existing deployment of LoRa nodes here, and we just capture real-world data, which is nice because it reflects the real-world conditions. But of course, it's very hard to control the signal-to-noise radio conditions. So we also wanted to generate simulated data with known parameters that we could use to study better these collisions. And we just model this as symbols with complex chirp with Gaussian noise, which is the kind of noise we would get on this kind of deployments. And after getting the data, we start with a very naive approach, which is okay. Let's just check the time frequency properties. Let's do a frequency analysis using the fast Fourier transform for getting the frequency spectrum, and the short time Fourier transform to get a spectrogram. And this was really naive because the expectations were completely different to what happens in reality. What we expected to get are very nice sine waves here, where basically we could kind of distinguish in the spectrogram what's going on, and we could kind of pick which is the full sine wave. But in practice, what we get is a lot of noise, a lot of carrier offset errors here that yield into something that is really hard to decode using simple techniques as thresholding. So at this point, we thought, okay, this is a kind of a complex problem, and maybe we can just start giving a look to machine learning, because in the end, find the full sine wave is harder than expected. LoRa collisions really yield a complex frequency spectrum. So at that time, we investigated a lot, and we realized that there was a hype of LoRa machine learning papers that claim to have very good performance, but most of them only work for symbols without collisions. So we thought, okay, this has the potential. Why don't we try this to actually try to identify which one is the full sine wave? So at this point, it's probably not bad to classify some terminology. Artificial intelligence is a broad term that includes many different techniques. Among them, there's machine learning, which focuses on learning automatically without being explicitly programmed. And also there's deep learning, which is a subset that uses neural network to learn complex patterns from data. Some authors use machine learning and deep learning interchangeable. Also, some other authors define deep learning as neural networks that are kind of big with many layers, but for the scope of this presentation, we will use the term deep learning for any kind of neural network. We just decided to go straight to deep learning, honestly, mostly because of the hype, because it's what people seem to be using, and because we're told many times in conferences that there are two types of researchers, those who use deep learning and those who are moving to deep learning. So it was kind of clear that basically we should try to give it a try. So as mentioned before, deep learning uses neural networks, and the main advantage is that this can learn from large and complex data, and it can extract features from data automatically in contrast to conventional machine learning techniques, where the features need to be extracted manually. And this is what makes them really powerful. But seen here in the figure, a neural network is composed by several layers of neurons, where each neuron is connected to all the neurons of the previous layer. This is an example of one input layer of a simple neural network. As we see, each neuron holds a value, and in order to calculate the value of the next layer, we just apply an activation function to the weighted sum of some weights of the previous layer plus a bias. And since there's a linear combination, we can represent this as a matrix multiplication. And if we stack this layer together, at some point we will get an output vector, which is could be a classification vector, regression vector, or any other kind of vector. And basically, the goal of the training algorithm is to try to find some weights and bias that represent a function that minimize the error between an expected output and the real output using a function law. So in the end, this is just a very complex nonlinear function, and we try to do a regression to actually fit this into this complex function. We also learned that there are many architectures of deep learning. Some examples, fully connected layers, which are these simple neural networks we show in the back. They are good at classification and regression, but we also have other models, such as convolutional neural networks, that are good at finding patterns in the data. There are also some that are good at predicting sequences, and recently there are autoencoders that are good at dimensionality reduction, and also they are used to do denoising, so remove noise from signals, which is something we will see later. So at this point, everything looks promising, and we kind of believe in this deep learning hype, and we just thought the process was kind of first gather data, build and train the model, evaluate the model, tune hyperparameters, and get state-of-the-art results. This was kind of our official understanding of how it works. So we just did a quick research and found that probably a convolutional neural network could work in our case, because we essentially want to try to match a pattern into so basically the pattern of the longest sine wave into basically telling which is the frequency that holds the bin with the highest energy. So the idea is, okay, let's train a convolutional neural network to find this longest sine wave. And we say, okay, let's use both the time and the frequency domain. Usually for this stuff, the time domain is really scary because of the noise, but since this seemed to be really magical, it was like, okay, let's just try to use the convolutional neural network just in case it learns the patterns on the time domain, which would be fantastic. And we also trained this from simulated data, mainly to simplify labeling and just to have a more realistic baseline. The architecture of this neural network uses convolutional layers to extract features, and here. And there's a fully connected layer at the end, which classifies the features found by the convolutional layers into an output layer that tells me which one is the actual symbol. We trained this for some time, and here are the first evaluation results. Time domain does not converge, and we say, okay, this is fine because the time domain is quite hard to unravel, right? I mean, there's only noise there. So let's see the other features. The spectrogram-based TFT, short-time Fourier transform, perform worse at the baseline decoder. And it's like, okay, this could also be because it's very hard to get a good trade-off between time and frequency. So this could also be the case, but of course, with the frequency spectrum, then we get all the information, and I'm sure this magical convolutional neural network should try something. But in reality, the frequency spectrum as input does not detect symbols with collision, which is basically the problem we're trying to solve here. But interestingly enough, it performs slightly better than the baseline decoder, which is probably a good result, but it's definitely not what we want, right? And I say, okay, the problem lies in the features. So probably the spectrum and the Fourier transform are not enough. So we say we need more features that are more powerful and capture more information. So we start a journey of some months trying different features such as the widely transform, the linear distribution, the synchronous transform, the fractional Fourier transform, the Hilbert transform, empirical mode decomposition, and many others. And say, okay, of course, here's the information we need in order to train a network and be able to find something out of there. We spent a lot of time on these steps here, and the aftermath is that, yes, some features yield slightly better accuracy than the baseline decoder, at the cost of a lot of computational complexity, which is, okay, the classifier also works best for symbols without collisions, which is a good result, but I mean, it's not exactly what we're trying to do here. So the gains of this approach just not justify the complexity of this network. So at this point, it became clear that just providing symbols to a black box was definitely not going to work. So we had different approaches, like, okay, what happens if we first try to identify the location of the peaks? We already have a convolutional neural network that we can use to actually do this task. And when we get the peaks, we say, okay, then just try to classify them, being a full sine wave. Based on peak features such as power, current frequency offset, this is something that has been done before in the research community. So it's okay, let's just take these features but apply machine learning to classify them. And this time, I mean, we noticed that it took some time to train the deep learning model. So let's say, okay, let's just try for this part to use a simple machine learning model, namely this gradient boosting strategy. And just to be on the safe side, I also wanted to compare it against a simple Bayesian or statistical method using z-score, so just a standard distribution, and see what happens. And the idea is that all this method would deal a probability, and we would choose a candidate with highest probability of being the full sine wave. So everything looks nice at this point. We start evaluating the peak detection, and it turns out it works. We can actually detect the peaks that we see here, and there, if we see it carefully here, there are many noise peaks that actually don't belong to any peak, but actually the convolutional neural network is able to detect, okay, this is a peak, but this one is not a peak. It has some false positive, but it's not too bad. And what is really interesting, there are cases where the actual peak is masked below the noise, and the algorithm is actually able to catch where's the original peak. So this looks really promising. We said, okay, we are just half done with our solution. And I hope we can say the same about the results of the peak classification, because what happens in the end is that the z-score method, so just not using any kind of machine learning, performs actually way better than our machine learning model, which also took some time to train and was a little bit frustrating because the z-score was probably something we've developed in 2 hours, and it gives better results, and it also renders better results than the baseline. But the state of the art is concurrent interference cancellation approach, which is not real time, but provides better results. So at this point, okay, we are getting somewhere, but the thing is, although the peak detection works well, it's computationally expensive, which is not good. And even our best classification strategy using the z-score doesn't bring any gains over the state of the art. And what we learned here is that the machine learning model performed worse under a simple method. And what is even worse is that performed worse than the baseline decoder. So this peak classification strategy just doesn't pay off. So at that point, it was already 4 months after we started the journey. It was clear that simple machine learning strategies were not going to work. We need to do something to make it better. And we were tempted to go back to conventional signal processing techniques, but the problem is the noise. The noise remains there. It's really the main challenge, and it's hard to remove using simple math because it's white noise, so it has all frequency components, and it's a very complex complex spectrum. So it's not as easy to remove. So at this point, we thought, okay, then why don't we just try a neural network to remove the noise from the frequency domain, and then we can even reconstruct back the signal to the time domain and try to do something interesting with a simple math techniques, which actually, since the problem is the noise, if we don't have the noise there, we should be able to solve the problem. So for that, we use the noise autoencoder. This is a very special architecture. It's built on top of an autoencoder, which is basically a neural network that tries to reconstruct the input, and here the output, through an encoder that compresses the representation in a few neurons, and then these neurons are expanded through a decoder to build again the output. What's the idea of this? Basically, what we are doing here with the standard autoencoder is doing dimensionality reduction. So we take the input and we just learn the key features in order to represent a signal, and then we can build it again. But the thing is that the noise autoencoder, instead of just giving the pure signal as an input, we give the signal plus a noise, and the output is just a signal. So basically, we are teaching this network to remove the signal from to remove the noise from signals. So we implemented this, and here are the first results. The evaluation looks promising. We see that basically the reconstruction is not perfect, but definitely the signal to noise ratio of the signal is increased. I mean, we can see here that most of the noise is already cancelled by this autoencoder. But what is also interesting to see that we kind of saw before of the convolutional neural network peak detector is that it's able to reconstruct peaks when they are affected by noise. So At this point, we were extremely happy because we said, okay, the signal-to-noise radio definitely improved. We can just start doing basic math. But since stuff cannot be that easy, there was a new problem that we couldn't foresee, which there was phase distortion because of the reconstruction problem. Who cares about phase distortion when we have the peaks? It turns out the location of the sine waves is encoded in the phase. So for instance, these two sine waves are clearly different, but they have exactly the same frequency spectrum and the magnitude, but of course different phase. And basically here we have completely different locations of the sine waves, and still we get basically the same frequency magnitude. The problem of this is that basically we lose the information of where the sine waves are. So basically, how can we detect which one is the longest sine wave if we cannot trust our own data? We tried different architectures and training methods, and it definitely improved the results, but in the end, phase reconstruction was still not good enough to actually try to do something useful. So this completely rules out the use of time frequency techniques in order to try to find something. So at this point, this was already 5 months after we started the journey. There was some light at the end of the tunnel at some point. For that, probably we should start with a recap. We definitely addressed this problem from many different angles. We were seeing that machine learning shows good results for certain tasks, which was quite promising. But again, this is not the problem we're trying to solve here. It didn't work for just trying to enable collisions. And the worst part is that each iteration took a lot of time and we didn't have any guarantee. So we knew that if we tried different architectures, it could get better. Maybe the solution is just around the corner, maybe not. We didn't know. And basically each time we tried to start with a new iteration, it could be another month just training a network to get maybe 2% of accuracy. And at this point was okay, do we want to spend more time on this? What do we want to do? And I say, maybe the problem is that we haven't found out how this works from the dynamics, and maybe it would be a good idea to try to go back to simple math, to actually try to start understand more the dynamics of a collision and see if there are other techniques where we could use machine learning more wisely. And this time also we have way more knowledge about signal processing. I mean, we now very good techniques to separate signals, to partition them on fractal spaces. So we have many different stuff that we can use now. And it turns out that after a couple of weeks of research, we finally identified an analytic scheme which exploits the structure of the symbol in a collision and isolates a full sine wave from the rest of the signal, which is essentially what we want, right? And we tested this strategy, and this was finally the time where we actually saw some light ahead. Here in the figure, we can see the symbol reception radio for the baseline, the state of the art, and our new approach. And what we see is that the symbol reception radio of our approach surpasses the one of the state of the art. This is on the simulated data, but basically this is also what we could see on the SDR data, which doesn't have all configurations, but this we could reproduce the result on real data. And what we find is that, of course, our new approach is a little bit more sensible to synchronization errors, but then we can translate the problem to try to synchronize better to the actual signal. And then we get an approach that can be used in real time, and that seems to perform quite well. And in the end, we didn't use any machine learning directly to get these results here. So here we go to the last chapter, which would be the lessons learned of this whole process. For that would be probably interesting to start with a post-mortem analysis. The thing is that we spent 6 months trying to solve a problem that could have been solved in 2 weeks using conventional math techniques, which sounds a little bit sad. And the question is, was it worth this time? My answer would be absolutely. Why? Because first, the knowledge acquired actually led to the final solution. It was impossible that we could just find this kind of strategy if we didn't work with the features, if we didn't work with all these kind of different properties of the signals. And this is kind of what led us to the solution in the end. And also, while we didn't use deep learning here, still deep learning shows promising results for several tasks, among them denoising and peak detection. And again, we didn't use them here, but this doesn't mean that we couldn't use these strategies for other use cases, such as peak detection in extreme noise environment. There are implementation of this in the research community, but we found some techniques that could complement our existing techniques, and maybe it's a good idea also to give them a try. But the actual lesson learned here is that although this thing is a really powerful. First, machine learning is not a silver bullet. It's definitely not magic, and it's not straightforward. This last item of being straightforward is mentioned all the time that, yes, sometimes if you have a very complex problem, machine learning can find a solution for you probably quicker than just trying to experiment with the model, but this doesn't mean it's straightforward. We'll see each item on its own. So this is not a silver bullet because it's believed that deep learning can do everything better than all conventional techniques. This is simply not true. There are certain tasks that are solved better with conventional math techniques. For example, most math tasks, frequency analysis, if I try to train a network to find the frequency components of a signal, it's unlikely that it will perform better as just doing a fast Fourier transform, for example. Also, training and tuning takes a lot of time. I hear that before starting this journey, but I thought, okay, we have enough GPUs, we have enough computing power, but this is not so much what takes time. What takes time is actually preparing the data, having to parse everything back, trying new models, trying hyperparameters, do this again, find bugs. This is a process that takes a lot of time, and in many situations, not always, but in many, you will get no more than 3% or 4% of better accuracy, and you already spent 6 months on a model that you could have just solved with a very simple model. Also, this was also one of our mistakes. This complex models do not ensure better results than simple models. This is especially true for deep learning models, because we heard many times that most researchers are moving to deep learning. It's true that deep learning can do very complex stuff, but this doesn't mean that it necessarily obsoletes machine learning or conventional methods. There are still many stuff that conventional methods will perform better than the deep learning models, especially if there's not so much data. And also, these complex models are usually harder to train, and this is time you have to spend when you're doing research. And you can already see if a model would not work if you just start with simple models. But of course, if your use case has to do with stuff such as large language models, such as ChatGPT, or if you have to do the noising in conditions where the noise is not Gaussian or has very complex patterns, or your use case is sketching Santa Claus drinking Glühwein in Hamburg, then of course, it's probably deep learning will probably be the best approach for this. The second big aspect is that this is not magic, because underneath the fancy names, machine learning models, especially deep learning, are just a bunch of matrix multiplications. And what this means is that sometimes days of training may convert just into a mathematical function that could have been written in a single line of code, but probably a single line of code takes you 10 minutes, and the other one takes several weeks until you get some useful data. And something that it's kind of obvious, but sometimes we also face this kind of issues, is that they cannot learn anything that is not in the data. And the problem with this is that sometimes you really don't know if your data is representative enough to try to actually solve a specific task. And also, they definitely won't replace domain knowledge. I mean, if you don't know what you're doing, it's likely that your model will just learn something that is absolutely not useful. And if you kind of guide it a little bit, it's very hard that you come to good results. And in fact, after some time, you kind of develop a sense of what is possible and what is not. And this is because in the end, it's just mathematics underneath. You can actually see, okay, probably if I have a function that is not convex and has some discontinuities everywhere, it's unlikely that basically a backpropagation algorithm for training the network would try to find something useful. Of course, this is not so easy to see when you have a huge model and many kinds of abstractions, but still this is math in the end. And what works on math probably will work here and the other way around. And the third item is that this is definitely not straightforward. What happens quite often is that the model may learn something completely different from what you expect. And really, this happened a lot. For instance, the first iteration of the autoencoder we had before adding the noising part just learned identity function. That means that basically our network was trained, learned to copy the input to the output. And this is pretty bad because it sounds funny, but it took quite some time to actually realize that this was the problem, because usually you have a training data and a validation data that looks kind of the same as the training data. And when we tried with the validation data there, we also got the validation data on the output and said, yeah, this is perfect, it's working very nice. And when we tried to actually fit features with that, we realized this doesn't make sense. You put an MP3 file here and you get an MP3 file here, and you put a picture, you get a picture, this doesn't make sense. And of course, it's just trying to copy the data. Also, what happens a lot is this mistake: if the data is not balanced, the model may learn to always predict the most common class. let's say you're detecting it to do, for instance, anomaly detection, and your data set has 99% of normal cases and 1% of abnormal cases. For the training algorithm would be actually a good bet if you always detect the normal case, because then you automatically get 99% of accuracy, right? And this happens a lot. And detecting these kind of problems requires some experience. And also there are many solutions to solve that, doing data augmentation, doing weighted training. But in order to know that that is a problem and how to fix that, it requires some time. So it's definitely not something that one would expect, okay, you start 1 week and the next week you will have useful results. Also, there's the problem of lack of interpretability, which I personally thought in the beginning, okay, if my model does whatever it's doing, I don't care so much if I cannot interpret the results because it's working. But in practice, what happens is that if you don't know what your model is doing and your model is not working, what can you do to make it work? You don't know why it's not converging, you have no idea. If your model is not giving you good results, how can you improve it if you really don't know in the direction you should move? And also the problem is architecture selection is really not straightforward. It's kind of known that there are some architectures that may perform better in certain use cases, but not necessarily. And there are authors that say that basically it's not possible to say, okay, this is the architecture you should always use for this use case. And even if you find an architecture, finding a loss function, activation functions, and also the topology and size of the network makes a huge difference. So it's very important to try many different networks at the same time. Try to find the proper hyperparameters, and before declaring a neural network model as useless, it's important to have the full hyperparameterization so you know that at least you're trying to perform something on the best configuration for the neural network. So we are approaching to the end of the presentation with the question, should you use machine learning? My reply is yes, but carefully. In my opinion, it's better to start with conventional techniques first. As mentioned before, there are cases where conventional techniques would work way better, not only in accuracy, but also they're faster, they are easier to implement, and they are predictable. And so if this works and you're happy with the results, better just not spend time trying to train neural networks or any other kind of machine learning model. If you're not happy with the results, or you like adventures, or you really insist, then at least try to identify tasks that may benefit from machine learning, which was one of our mistakes. If you have some problems such as pattern recognition, prediction, or maybe if your problem has to do with generative models, then it's likely that machine learning could do something for it. But if you just expect that basically you would keep your data and the output will be your written paper, this is definitely not going to work. And also, it's very important, and I cannot stress this that much, that it's very important to start with simple models before moving to deep learning, and especially if data is limited. Sometimes simple models give an idea of whether this could converge, and it's advisable when you already find some good results. With machine learning, maybe give it a try to deep learning to see if the results improve a bit. But in many cases, you will already find that this wouldn't work if the machine learning models also don't converge at all. And in general, it's better to try many models at the same time. This is very simple to do with modern frameworks. Basically, you're just allowed to use in parallel many different machine learning models. And basically, you just have a nice interface and you can try 10, 12 different machine learning strategies because they all work differently depending on the use case. And it's better to just have all these models before doing the decision of trying to go to a more complex model. And that's the end of my presentation. Thank you so much for your attention. I'm open for questions.
Did you have some conversation with some ML experts over your problem?
Yes and no. I have some. I joined this ML group. Mm-hmm. Yes. There was a scheduled presentation at some point, but unfortunately there was a time where I had to move somewhere. Then I joined there, and apparently it was not scheduled. So basically, I couldn't interact directly with the experts. What we got from this group is basically the server that we use for training the machine learning algorithm, which really helped us a lot. Mm-hmm.
Given the input data, is this like a task that for humans is solvable? easily, or is this more generally challenging? That if you would just look at the data on both sides, could you do this kind of by examining the data set carefully, or is this a thing that is just too hard to do?
When the signal to noise ratio is high, then yes. When you have a very low signal to noise ratio, so you start confusing a lot of peaks from the noise with peaks from the actual signal. And in the phase of these peaks is encoded that they are actually a full sine wave. And this, we saw that this was detected by the peak detectors, by basically some algorithm, but just seeing with raw eyes, it's very hard to know, okay, this peak is actually not a component of noise, but this is actually a peak of the full noise.
Maybe just a comment. I mean, at least in my case, I hit many times the complexity not only of the models themselves, but also of actually making this work and actually using the data correctly, which can be also pitfalls because, well, you think everything is working and suddenly it's like, oh, well, my data sets were actually not right. That's pretty common. I mean, so what would you say would be like a maybe good advice or things to actually follow besides knowing your models and knowing what you're looking for, more about like in the practical side?
I think the practical side is very good when the testing procedures, I mean, basically for testing your model, of course, not with the data used for training, because otherwise it would create bias. But I think it's very important that this data is really, or this method for evaluating your model is completely orthogonal to your main code. For instance, I have many times a problem where, because of misunderstandings of the PyTorch API, I actually mixed the validation and trained results. On the first result for the FFT, I got 99.9% of accuracy.
Yep.
Already we're publishing the paper and everything's nice. And I put a paper with the software-defined radio, just to realize that basically I use the same trained data to basically just learn to work with data. This was a misunderstanding. So if you can have everything orthogonal, I think it's very, very good because at least gives you a layer of security.
Some other, I mean, you mentioned some things of overfitting. Some other experience of overfitting you had?
Oh, yeah, several. I mean, the first version, for instance, of the autoencoder, I got an extremely clean signal that looked almost suspicious, and it was the same thing. Basically, there was a kind of misunderstanding of how the API of this partition function works. So basically, it was every time getting half of the data set on the validation as well. So we used the same data used to train for getting the values. And then, of course, I got a perfectly reconstructed autoencoder, and that basically this was kind of what fueled to go with autoencoder, because I said, okay, this looks really great. I mean, I can reconstruct the full signal even under very heavy noise. Yeah, this happened a lot. I mean, in the end, I implemented some stuff that tried to help me to avoid doing these kind of mistakes. But the main problem is that usually when you're doing this with conventional techniques, you would immediately notice there's something going on wrong. But here, it really takes a lot of time until you can say, okay, this was not trained properly. This is definitely an error of input data. Also, what happens is you have to be very careful in how you process the data. At some point, I noticed I had some bugs from the real. I mean, when pre-processing the data from the captured data, so real world data, actually I didn't implement it in the right format that the input layer of the neural networks expected, and I was getting bad results on the models, while I was getting good results with the tested data, basically. And also to realize that there was a problem with formatting the data from the SDR also took some time. So basically, this wouldn't happen with a conventional signal processing technique because you can actually see what you're doing.
So, Jose, I mean, if somebody is not good in math, you wouldn't advise to him to use machine learning, right?
It depends. I think it depends. I mean, there are tasks. I mean, basically, what I wanted to say with this whole thing is that not every task will be solved better with deep learning, but there are some classification tasks that would be very hard to do with conventional math, that you could do with simple machine learning models. And probably you don't need to be that into math. I mean, at least understand the basics. Of course, it helps, but I don't think you need to be an expert in linear algebra or something to use these models.
Yeah.
But having understanding, of course, helps a lot.
But if you want to take a more challenging aspects, then I mean, this is one of the takeaways, that you need to understand the logic behind. And for this, you need to understand the math as well. So
yeah, it helps. I mean, on the other side, for many simple tasks, it's kind of well documented everywhere. I mean, there are many simple machine learning models that people just grab from known sources. For this kind of stuff, probably you don't need to understand that much, but usually if you want to try to go beyond the boundaries of simple models, it definitely helps a lot. I mean, knowing some statistics also gives you a sense of what is possible and what is not. For instance, what I mentioned before with this case of complex functions, for instance, if your output function is really something that has no relation with the input, then the neural network won't be able to do anything. But in order to know that it won't do anything, you have to understand a little bit how it works. It also helps with the training process, because you know that basically training with this backpropagation is using gradients, for instance. And you know that under certain circumstances, you won't get anything, but before you try them out, if you already know kind of what is happening there, it definitely helps. But I don't think it's that big of an entrance barrier, in my opinion.
I have a more generic question. I mean, what we see these days is a lot of people running around solving problems with machine learning and claiming these fantastic 99.9 something results. And probably they're convinced of this, and probably there are a lot of, I mean, a lot of them fell into traps and just, as you mentioned, had some fake results. Could you think of some generic method to sort of counter check? So could you give an advice? I mean, if you know the problem in detail, that's different anyway, but would you give a generic counter check that helps to sort of identify these sort of traps?
I think a very generic mechanism is a little bit complicated. There are definitely stuff that can be done, but I think they're always domain specific. For instance, on this case, I mean, for many of these LoRa machine learning papers, basically it's curious that some of them just use one kind of data representation, so a fixed signal-to-noise ratio. And probably the first test one could do to counter-check this is to actually validate the model using at least clusters of configurations. For instance, if you're doing LoRa decoding, at least try a case with high signal-to-noise ratio, a case with a fraction of frequencies, a case with low signal-to-noise ratio. And with that, I mean, this is in the end what we had here in the models, and this definitely reveals that there are some problems with the underlying neural network. But it's really domain specific. I mean, probably in some other cases, if you're measuring network traffic, you would need to at least identify cluster or simulate some data that basically you could feed in. And
but that would mean, I mean, the approach is a little bit like scaling the problem. So trying to apply your machine learning to sort of different complexity levels and see whether the output behaves as expected. Yes. So the problem gets harder, the results should get worse. Right?
Yes, yes. Yeah. That's at least to avoid this problem of overfeeding a certain condition.
Yeah, yeah.
Yes, definitely.
Yeah, it's at least my bet on this is that we in 5 years learn that 80% of the machine learning papers are just wrong.
I think the problem is because I mean, the problem is mostly, as mentioned before, it's just a hype. I mean, not because you can do something with machine learning, it means that it performs better. But there are cases where definitely the only way to do it properly would be using machine learning or deep learning strategies.
Yeah. No, my problem is I believe many people just run in these traps and then they stop and they say, okay, I'm finished. So yeah. 99% accuracy.
Yeah.
Couldn't do better.
And also I think it's important to understand the limitation, because still, I mean, if you're lucky that your whole program is describing a data set, it could be that basically you don't need more than that. But if you have other cases that were not on your data set, it's impossible that the neural network or any machine learning model learns how to properly do it.
so everybody overwhelmed.
Another question, in the slide with the denoising process and the raw data process of frequency, why is there a difference between the two first peaks?
This one?
Yes. Is that the start behavior of your model, or why you got the lower peak than the raw data?
Yeah, this is the point where basically mentioned before that one of the complications that it's very hard to understand why render the results. I suspect that this reason is just because we try to normalize the function on the input, we normalize the whole signal and not just chunks of a signal, because we noticed when we took, we were using a chunk size of 16 bit here to reconstruct the whole signal. And if we normalize each chunk size, then the output really will get through noisy. So the strategy we were doing here was just to normalize the whole signal and just put it there. And I believe this has something to do with the fact that in some cases where there's not so much noise around, it could think that basically it was a peak with not so much energy, and probably it's just a matter of how it was trained. And basically this is the distortion I was talking before. With the other models, this is the first iteration, it definitely got better. Then we could actually reflect more the real peaks. It matters, also the signal to noise rate of this signal is also not, this is a lot kind of low signal to noise rate signal. And it could be also that some of these differences are because maybe on this peak there was also noise. In this case, it's definitely not noise, but it's probably mostly because of the normalizing process.
Do you see something interesting in the latent space in this autoencoder? Because this is already output, right? Of the was there some nice or like some feature that would work?
Yes.
Okay.
Yes. In fact, it was very nice to find the position of peaks.
Okay.
It was actually easier to train a network with very compressed representation.
Mm-hmm.
And I just gave it a try to basically see if I could get the peak position, and it worked. But since we already have the peak detector before and detecting peaks doesn't give you the final solution, I just didn't continue that. But actually, it was a very
so it was actually encoding the position.
Yes, encode the position, which was very good in the end, because probably if I did the peak detector again, I would definitely try to run an autoencoder first to do this dimensional introduction and training from the data where this definitely works. It's also, it's not that easy to make an autoencoder convert. But this is something you can just leave unattended until you find something. And when you get this latent space, you can then use it for training your data with a more compact representation. And you can always try to reduce the latent space. So then you make it even easier for another model.
Okay.
I have a question too. You went over it for a reason, probably, but I'm a bit interested in how you actually solved the problem in the end, like the simple math approach that you took. Could you summarize it in some words?
Yeah, what we did there, the idea is that basically you had a full sine wave. You know that at least on half of that you will have, the full sine wave that shouldn't change its basically its amplitude throughout the whole symbol. And you know that if you have an odd frequency, for instance, you could just split your symbol in half, and you know that if you add the first half with the second half, basically this half sine wave would cancel out only if they're a full sine wave. You see what I mean? And you can do something similar for basically for even frequencies, and in the end you can build a kind of filter that basically would only work if the signal is a full sine wave. And with this information, basically you can extract the full sine wave.
Nice.
Everybody quiet and impressed, I guess. Yeah. No more questions? Remarks? Anybody who has excellent experience with solving problems with machine learning?
Mhm.
Well, at least Leandro had some okayish experience, right?
It was not magical though. It's
It was not magical, it was a lot of work, right?
Yeah.
Was not
So-
easy.
No.
Okay, then thank you again.